Okay, guys, we're off to a new chapter. Let me give you a little preview of what this is about, or some reasoning. Let's start off with a differential equation that we all know. So this is chapter 7, and let's start off with a differential equation that we know. I don't know any more differential equations. Let's start off with something really simple. Y prime plus y is equal to 0. So this is the same thing as y prime is equal to negative y. This is a first order. It's linear. It's autonomous because there's no x's in there, or t's, whatever the independent variable may be. And we know the solution to this, right? What's the solution to this? Y equals what? No? No? Close, yeah, e to negative x. So let's throw some constant in there, c times e to the negative x, or let's use t. For the sake of this particular chapter, we're going to move our independent variables to t. So this is what we've been doing here. What we've been doing is this blue arrow, doing I don't know, separable first order linear, and then we went to second order. We did some other techniques, whatever other techniques that we've done. Etc. as etc. So there's a lot of techniques that we're learning and that we've learned, including power series, by the way. So we can add that onto the list. Some undetermined coefficients and variation of parameters and stuff like that go in here too. So so what this is like the t world, giving our independent variable t. I want to call it the t world, where in the t world, we're going to go to another world, by the way. In the t world, we use calculus. So all the stuff that we're doing, we're integrating, we're using calculus to solve for this stuff. What we're going to do today is we're going to go to another world. We're going to dip down to this other world that for now we'll call the S world. And in the S world, we're going to solve for some mathematical stuff, but instead of using calculus, we're going to use algebra. And algebra is easier than calculus, right? Sometimes. Do you guys remember how to complete a square? Okay, so that's the algebra. Do you guys remember partial fractions? You might think that partial fractions is calculus, but it's really algebra. Right? Except we didn't see it until we saw it in Calc 2, where we had to do partial fraction decomposition. But that portion of the work that you did there is just algebra. And then you took the integral of these simpler fractions that would, a lot of them turned out to be ln of whatever. But it's really, the work is algebra. So what we're going to do is we're going to transform. In between these two worlds is a transformation. We're going to transform from your t world into the s world by doing, in this particular case, a Laplace transform. And then we're going to, let's see, the notation for this is to use the same variables except we use a capital Y with some other stuff in it with a Y. And then we're going to solve for this using algebra until we get something, a solution that we'll call y, capital Y of s. So this y over here, the little y's with our t's get transformed to a capital Y. We do some algebra to that to solve for y. So this part that we used to do when we use calculus and all the techniques that we've learned, we can now take that into this transformation. So there's one other part left to get our solution. And what is that? So we started here, we switched worlds to the s world, we used algebra to solve for y of s, and then what? You have to go back. You have to transform back. We have to transform your answer back to the s world. Okay? So that's a quick overview. And so the key is to figure out what these transformations are. Okay? So for that, we will need calculus. We'll need integrals. And specifically, we're going to need integration by parts. So I hope you guys remember that stuff. All right, let's take a look at the definition of a Laplace transform. I have to undo the proofing here so I don't have the little things underlined. So here's our first definition. Oops. Our first definition is a definition of the Laplace transformation. So we have a function f, we'll call little f of t. Then we're going to transform that into capital F of s. So this is where we go from the t world to the s world. So in t, we have some function, whatever that might be. It could be a constant. It could be t squared. It could be sine t. It could be e to the t. It could be one of those things. And that is sitting in our t world. And then we're going to transform it to go to the s world. Okay? Now, this is defined by an integral. And what you have to really be careful is to notice where the variable, the integrating variable is. That's t is your integrating variable. And when you integrate with respect to t, and then you evaluate it at these limits from 0 to infinity, an improper integral, then it's going to lose all the t values. All the t values will disappear. And then you just have f of s, a function of s in there. Okay, so one of the tools that we need is to take a function in the t world and see what that becomes in the S world. All right? And so the easiest function to look at is 1, a constant. So let's take a look at a few examples of some functions and get ourselves kind of sharpened with our integration by parts. All right, you got this transformation memorized now? Integral from 0 to infinity of e to the negative s times t times f, the function that you're transforming, f of t dt. Okay, let's take a look at how things would look like, how we're going to transform things. Let's take a look at f of t is equal to a constant, and the easiest constant would be 1. So the transformation becomes an integral from 0 to infinity of e to the negative st times f, which is 1 dt. So what is that? Well, we don't need anything fancy here. Maybe just a simple u substitution. Du is equal to negative st, and then, or u is equal to negative st, and then du is going to be a negative s. So that's going to give us a 1 over s constant with respect to t. Zero to infinity, and then this is going to be negative 1 over s e to the negative st, evaluate from 0 to infinity. And you know, technically when you do this, you're supposed to take the limit as b goes off to infinity, and then let this infinity be b, and then let it go. But we're going to do this a lot, so let's just say what happens if you put infinity into the t value. Remember, this is a t. If you put infinity in for t, this is going to go off to negative infinity. E to the negative infinity is what? It's what? 0. Okay? So this is negative 1 over s. And then if you put the top limit there, it's going to go to 0. If you put 0 in there, what do you get? 1. So minus 1. And then, so negative and negative becomes a positive. This just looks like s, positive 1 over s. Okay? So our constant 1 goes to 1 over s. So in the t world, you're 1. In the s world, you become 1 over s. Now, there's a special notation for this, and I've already kind of alluded to that with the capital letters and with some other stuff. But there's the formal notation is they use a fancy L. I couldn't find a nice fancy L in my computer, so I have this L over here, which isn't the kind of L that usually denotes Laplace transforms. I'll draw it in a minute, but I wanted to put this here. So in terms of my notation in my notes, you'll see this, but when I handwrite it, you'll see this is going to be the notation. So we're going to take L. This is the Laplace L that's used in most books. An L, and then sometimes they use square brackets, sometimes they use curly brackets, and then they put the function in here. So L of this function 1 is equal to, and then this is the function 1 over S. All right, let's do another one. Let's just do a linear now. Let's do t. So what is that? Again, we start off with your integral transformation going from 0 to infinity, e to the negative st, and then now your function, instead of just a regular 1, we actually have a t in there. That's your f of t, dt. And so as I look at this, I think, oh no, this is an integration by parts. And so if we remember integration by parts, we have a u and a dv, I think. At least that's how I learned it. The u is something that you would take the derivative and hopefully over time it'll disappear. So du looks like it's going to be equal to dt. And then now our dv would be the rest of it, which is e to the negative st dt. And the antiderivative of that gives us our v, which is negative 1 over s e to the negative st if you do a u substitution. So that gives us uv. So it's negative, I'll switch the order here, 1 over s times t e to the negative st minus the integral of v du. Now v du has a negative 1 over s. I'll not combine the negative signs yet. I could, but we'll do that a little bit later. And then we have the integral from 0 to infinity of e to the negative st dt. Now, this is, hey, we just did this up here, right? Well, at least it's equal to this without putting in the limits yet. Let's put in the limits towards the end. Let me rewrite that uv again, 1 over s t e to the negative st. And then now I'll put a plus here, 1 over s. And then this whole integral here that I underlined is equal to negative 1 over s e to the negative st. We could have taken this, by parts. The first part, taking the limit from 0 to infinity, and then we could have just gotten the final answer for that one. But let's do it kind of slowly here. So we're going to put infinity here. Now I'm just going to kind of walk through this and see what happens. And this is not the thing to do, but I'm going to do it anyways. Putting infinity here, we're going to get infinity divided by well, I was going to say this e to the negative st is like e to the st in the denominator. So if I put infinity in for t, infinity in for e to the negative st, it's infinity over infinity. So you can technically take what rule are we talking about? Infinity over infinity? L'Hopital's rule. So the denominator is going to go to infinity faster. So this whole thing is going to end up being 0. Minus putting 0 in there, we're going to get 0 for t. So this is going to be 0. So let me just put a little justification here. E to the st goes to infinity faster. And so that's going to be 0. So what do we have left? We have negative, well, I'm just going to put 1 over s here. and then see what this goes. Well, that's kind of like the same amount of work that we did up here. We did this already. It's negative. Oh, that's just 1 over s. So this whole thing becomes 1 over s. So we end up with 1 over s squared. Does that look good? That looks good. So your Laplace transform of t, if you're t in the t world, then you're going to become 1 over s squared in the s world, provided that we did this integral correctly. Did we do this integral correctly? Yeah, we did it correctly. All right? We could do this for t squared and t to the third and stuff like that. Should we do it for one of those? I guess if we do it for like t to the fourth or something like that, I get to show you this pattern, and I don't know if you learned it in your Calc 2 class where you have to do integration by parts multiple times. See this nice little chart. I didn't learn it like that myself, but I thought it was kind of cool when I saw it. So let's say f of t is t to the, let's go to the fourth power here. So our integral would become, the Laplace transform would become 0 to infinity of e to the negative st times your f of t function, which is t to the fourth dt. So this looks like it's an integration by parts problem. But now I can kind of see that if I let u equal to t to the fourth, the du is going to be equal to 4t to the third, and I have to use integration by parts again. So there's this cool little pattern thing that I saw one time where you have a list of u's and v's. I don't know if they call it u's and v's. But you let your u equal to what you would let your u equal to initially, and then your v equal to the rest of the stuff. And then on one side of this, you take derivatives. On the other side of this, you take integrals. And the idea is to take derivatives until you're done, until you stop. So derivative, derivative again, 12t squared, 24t, and 24. And then eventually you'll be done with 0. And then on the other side, you take antiderivatives. And each time we take an antiderivative, we're going to get a factor of negative 1 over s, right? So negative 1 over s, e to the negative st. Now I want to take the antiderivative of that, keeping the negative 1 over s, so it becomes positive 1 over s squared, e to the negative st, and I keep going. Then I don't know if I go one more. I think I go one more. So negative 1 over s to the fifth, e to the negative st. All right, so what I have here is a list of derivatives and integrals, and I combine them by looking at not directly across from each other, but one down. And then each time you apply your integration by parts, you introduce a negative. So it's uv minus vdu business, so you introduce a negative. So the first one's going to be positive, and then you're going to have your alternating signs here. For those people that really know how to use this, am I doing it correctly so far? Never seen it? Yeah. All right, so what you're going to do is combine these products. So you're going to have t to the fourth times negative 1 over s e to the negative st minus 4t to the third, and this becomes positive 1 over s squared e to the negative st. And then I have a plus 12t squared. And then now this changes to negative again. S to the third e to the negative st plus 24t. Positive 1 over s to the fourth e to the negative st. And then I have one more. All right, my signs. So this is a negative. Positive, negative, positive, negative, and the last one's positive. 24 times negative 1 over s to the fifth e to the negative st. Now I have to take the limit from 0 to infinity. So if I put infinity into all these t's, now remember these are t values. If I put infinity in for all these t's, let's see what happens. I'm just going to take a sample and just take maybe focus on this one, and then we'll see that for most of them it'll be the same way except for that last one. So if I imagine taking this thing, negative 4 t cubed, negative 1 over s squared e to the negative st, and I want to see what happens when t goes from 0 to infinity here. Before I do anything, I'm going to rewrite it. This is positive. So negative 4 over s squared are constants because t is the variable. I have t cubed, and then I have e to the st. Now that I brought it in the denominator, it becomes positive power. And then I want to see what happens when I put infinity in there. So this is a thing. You take the limit as b goes off to infinity of, I want to ignore the constant. I just want to look at the variables. I have b cubed over e to the 3b. And what happens is that if you use L'Hopital's rule, this denominator is going to go to infinity a lot faster. If you use L'Hopital's rule, you'll eventually get 3 or a constant, 3 times 2. You're going to get like a constant up on top, and the variable still here going off to some constant over infinity, which is going to take you to 0. So at infinity, you go to 0. And then if you put 0 in for t, it really doesn't matter anything else. Nothing else matters. If you put 0 in for e to the t here, the e to the 0, which is 1, and then you have 0 cubed, which is 0. So this is also going to be 0. So this whole thing is going to go to 0. And by similar arguments, most of these are also going to go to 0. Except for this last one. Let's see where this one goes. This one doesn't go to 0 because when you put t in there, when you put t is equal to 0, there's no t variable hanging out here, right? So let's take a closer look at this and see what happens when you put infinity in 0. So if you put infinity, this is going to go to 0. So let me rewrite it as negative 24 over s to the fifth. Let me just write e to the negative st here, going from 0 to infinity. that's going to equal to, if you put infinity in here, this is going to get closer and closer to 0. E to the negative infinity goes to 0. So the first part is going to be 0. And then if you put 0 in there, if you put 0 in here, it's going to be e to the 0. And what's e to the 0? That's just 1, right? So it looks like the negative negative will cancel. I will have a 24 up in the numerator and a s to the 5th down in the denominator. And that is my transformation. So Laplace transform of t to the 4th is equal to 24 over s to the 5th. Uh-oh, my s and my 5 are starting to look alike. S 5. So we saw a couple early on, and we probably could have done all the other ones, but can you guess, maybe? 24 seems like it's a weird number. Where'd that come from? Where did 24 come from? Let's see. 1 times 4, 4 times 3. Hey! 12 times 2. 24 times 1. Can you give me a pattern for this? N factorial over s to the n plus 1. Bam. Okay. Now, if you're a math major, you would prove this by induction. I'm just saying. Okay, so now we have a nice pattern for this. We can go on and do some more, or I could just tell you. I could just tell you. There are going to be limitations. We're going to be bound to a certain amount of functions that we can transform. There's going to be other more complicated functions that we might not be able to transform. But I think in general, we get to see the more basic ones that we've seen a lot of already. So I was going to do e to the 4t and cosine to the 3. Let's do one more. Let's do either e or cosine. Which one do you guys want to do? Cosine? Yeah, of course you guys are going to pick that one. And what if I just tell you? Do you remember e to the t times cosine t? Remember integrating that? You integrate it, and then it looks like there's something else that we're looking for. It's like a roundabout integration by parts. All right, let's do it. Fine, let's do it. F of t equals cosine of 3t. I'm really just tempted to look at the formula for this, because there is just a formula for this. Let's see how far we can get before I get impatient. I'm already impatient. So this is what you're looking for. Let me, because I think the way the process goes with this roundabout way of integrating, this is what we're looking for. This is the Laplace transform of cosine 3t is equal to this integral. So what we're going to do is we're going to integrate by parts. And I'll try to use that thing. Actually, I'm not going to be able to use this, and you'll see why in a minute. But let's see if we can take advantage of this anyways. So in this case, e to the t, when you take integrals or derivatives of that, it just remains the same. And the sine and cosine, when you take integrals and derivatives of that, it kind of bounces back and forth. And so in this case, it doesn't really matter which one you use for u and which one you use for dv, as long as you're consistent with it. So let's just say e to the u is equal to e to the negative st. So let's take and then the dv is going to be cosine 3t. So du is going to be negative s e to the negative st. We're taking the derivative with respect to t. I don't know if I need to go one more, but I'll go one more. Negative s squared, positive s squared, e to the negative st. And what happens here is that when you take the antiderivative, you get a factor of 1 over 3, right? So 1 over 3. Now the integral of cosine, is that positive or negative sign? Positive? Yeah, I think that's positive, right? Be careful when you're integrating and taking derivatives of sines and cosines, because they have different rules. So I think this is positive sine 3t. And then now the integral of this is where you start getting the negative. And then another factor of 1/3. That would be 9. And if I do this matching up one down, I'm going to see that I get the same thing again. If I keep going here, I'm going to start getting sines and cosines put together. So what I'm going to do is I'm going to stop it somehow, and I don't know how to stop this using this little technique here. But I think, let me give it a shot. So this is going to be equal to u and v. So that's e to the negative st, that's u, and then v is going to be 1/3 sine 3t, minus the integral of v du, and this is du over here, and this is the v, the integral of that is this. So I'm going to go down here and write negative s e to the negative st times negative 1/9 cosine of 3t. And then the thing about this is that I can keep going, but the integrals are just going to be repeating sines and cosines. So what I'm going to do is I'm going to stop right here. Let's see if this makes sense. I'm going to stop right there, and I'm going to call this a positive integral of s squared e to the negative st times negative 1/9 cosine 3t dt. So I hope I did that right. I want to make sure that negative is clear here. So what I have is, if I filter things out of this, let me see, let's simplify this first. We have 1/3 e to the negative st sine 3t plus, or minus, minus, and a minus. There's 3 minuses here, so I'll say negative s over 9 e to the negative st cosine 3t. And now I'm interested in taking out all the constants that are available here. So available for taking out. So I have a negative 1/9, and I have an s squared here as well. So after I take out the s squared and a negative 1/9, I would just have e to the negative st cosine 3t dt. Now guess what? That's what this whole thing is equal to. If we include the limits, add it to the other side. So these two are exactly the same. You can call it A, or why not just call it L. And add it to the other side, which means we need to add the coefficients. Right? So we're solving for this box over here. And that would give us 1 minus negative 1 over s squared over 9 is equal to the rest of the stuff that we didn't really mess around with. Say it again. Plus. Okay. So then you would divide by this whole thing, by this. Let's find common denominators for that. This would be 9 plus s squared over 9. Is that right? So if we divide by that, it becomes 9 over 9 plus s squared. Is that correct? And so I'm just going to rewrite everything else. Hopefully my signs don't make a mistake along the way. And remember that we want to take this from 0 to infinity. All right, let's see what happens when you put infinity in there. So I'm going to rewrite 9 over 9 plus s squared. All right, let's put infinity in. If you put infinity in, e to the infinity is just going to oscillate between 1 and negative 1, right? And then you have e to the infinity, e to the negative infinity that's going to squeeze it down to 0. So if you imagine this oscillating thing getting squeezed down to 0, as it goes off to infinity, it just becomes 0. So that goes for both of them when you put infinity in. And then let's put 0 in. E to the 0 is 1. Sine of 0 is 0, so this goes away. And infinity, or 0, in for t is e to the 0. Cosine of 0 is what? Cosine of 0 is 1. So I think that'll have to stay. All right, we did it. This becomes a positive. Negative and negative becomes a positive. It looks like my 9s will cancel, and then I just have an s in the numerator and a 9 plus s squared in the denominator. So this is the integral, right? But that integral is also the Laplace transform. So what we've essentially found is the Laplace transform of cosine 3t, and that is equal to s over 9 plus s squared. Now take a guess. I put 3 in there initially, but what if we change it to 2 or 5 or a? What do you think the transform is going to be? S over a squared plus s squared. Now just try to look to see if it matches. It looks like it's good. Then this must be the transform. All right. So what we're going to do is just like you build a table of derivatives when you first start taking derivatives, right? You found out the derivative of t to the n power is n t to the n minus 1. You found out the derivative of e to the t is e to the t. You found out the derivative of sine t is cosine t. So you start building a table from what you know. And so that's what we're going to do is we're going to build a table. Or I can just copy a table from the book. We have a few of them already. We have 1, we have t to the n, and then now we have cosine 3t. So I think that's enough. We can just let you in on a handful of some basic transformations. So here's a handful that they have. We can certainly build more. Notice there's a slight difference between sine and cosine, and then they threw in the hyperbolic functions over here too. But the cosine we did, we had s over a squared plus s squared, and they use k here instead. But the sign's a little bit different. It's a constant. It's k over s squared plus s plus k squared. And then the exponential function was an easy one that we didn't do. You can look at the book to see how they did it. The sinh and the cosh are, if you remember what those are, a sine hyperbolic function. Sinh of t is e to the e to the t minus e to the negative t divided by 2, I hope. The cosh function is e to the t plus e to the negative t divided by 2. So the sinh and cosh function are just defined from the exponential function. All right, so you know that integral stuff that we did, that you guys will never have to do that again, unless I ask you on the test situation to prove that the Laplace transform is something else. But in general, when you guys are doing these problems, you guys are in physics and engineering classes, and you have to do a Laplace transform so you can solve for differential equations, you're not going to rederive this thing. You'd look at a table like this and say, oh, I need the Laplace transform for sine 2t. You would just look at this and say, okay, the Laplace transform is going to be 2. I divide by s squared plus 4. And so that's how you would do this. But I think we just did some Calc 2 practice with what's that called? Parts, integration by parts. All right, so that's how we take things to the t world. We're missing something, though. Oh, wait, before we go on, this is a transformation that takes a function in t and gives you another function in s. So this is a transformation. And we've had other transformations where you have a function in t and you brought it to another function in t by taking the derivative or the integral. Right? Those are just other transformations. This particular transformation is slightly more complicated. And there are more complicated transformations also. But it's basically just a transformation. And there's one important property in this transformation that allows us to string a bunch of other things. Like at this point, if we know all this, we technically don't know how to transform t to the third plus 5 or 4t squared minus 1. We technically don't know how to transform this. We could probably guess that we can just split this up and then take out the constants. But allowing you to transform this into L of 3t or t cubed plus 4 L of t squared minus L of 1. This here, this equal sign, is not confirmed until you know one more important fact about this. And one important fact about this is that the Laplace transform is a linear transformation. So let me copy this again onto the next page where I'm going to say linear transformation. So Laplace transform is a linear transformation that allows us to break up functions, as long as you're adding and subtracting them, and then take out scalar multiples. So we don't know the Laplace transformation of this whole polynomial, but now, because we know each of those power functions, then we know the Laplace transformation of these polynomials. We also know the Laplace transform of e to the t plus 4 cosine 3t, and that's equal to the Laplace transformation of e to the t plus 4 and the Laplace transformation of cosine 3t. So those we take them for granted, and we're going to come back and take it for granted again. But before we take it for granted, we should know that it comes from a special property that the particular transformation we're talking about is a linear transformation. That fact that you're integrating a constant times a function, you take a constant out, is because integration is also a linear transformation. The fact that you're taking derivative of sine plus cosine when you're adding or subtracting, you can just take the derivative individually, means the derivative is a linear transformation. So likewise, this Laplace transformation is actually a linear transformation that allows you to break things up like this, as long as you're adding and subtracting. Now be careful. This applies to addition and subtraction and scalar multiplication, but if you're multiplying two functions together, this is not, and I'm going to put a big not here, e to the t times L of cosine t. This is not. not. It's not. So multiplication doesn't apply to linear transformations. Scalar multiplication, when you have just a constant out in front, that's not a big deal. But regular multiplication doesn't work. Let me write this a little bit neater. Okay, so that's the property, the linearity property we can now exploit. Okay, there is one more thing missing, aside from a bunch of other functions. They kind of don't talk about it until the next section, but I should bring it up now. The fact that we are taking we're taking differential equations into the S world means we probably should know a little something about derivatives. We probably should be able to take a derivative of some unknown function into the S world. Right? So, let's do that now. We know that if we have, we know that we have f. I'm going to write it slightly differently here. I'll write it somewhere. L of f of t gets sent to, and this is a notation, capital F of S. And then we know that the way we get to that is by doing this integral. What's the integral again? Oh, e to the negative st f of t dt. Okay, so we know this is a Laplace transform. So what I would be interested in or curious about is what happens, or how do you take a derivative into the S world? Well, let's find out. All we'd have to do is pass it through the linear transformation, right? E to negative st. Now instead of f of t, my function is now f prime of t. That doesn't look that helpful. What if we use integration by parts? Now, f is some arbitrary function that I don't know of, so I'm probably not going to be able to get rid of that, or f prime here. But what if I take the antiderivative of that? Let's see. If I let e to the st be the u function, and the dv would be f prime of t dt, then du is going to be, wait, this has a negative, right? So du would be negative s e to the negative st dt, and then v is equal to what? Just the antiderivative of f prime, which is just f of t. That's looking good for me, I think. All right, so according to integration by parts, I have the first integrand, the integral is going to become uv, So I have e to the negative st times f of t without the prime, because I took the antiderivative, minus the integral of v du. I have a negative s. Let me write it like this first, and I'll simplify it later. This is your du, and then this is your v, f of t. All right, now I want to take this e to the negative st f of t from 0 to infinity. We'll deal with that in a minute. But now on this one, I could take out any constants that I have, because integration is linear. I have a negative s to take out. That would make this a positive integral from 0 to infinity of e to the negative st f of t. That looks familiar, doesn't it? What is this equal to? That's equal to big F. Now how about this business over here? Let's figure out what's going on over here. I need to put infinity in there, e to the negative infinity and f to the negative f to the infinity. Well, as long as this exponential function goes off to infinity faster, this is going to go to 0. So this would be 0 minus, now let's put 0 in there. Does that disappear? It doesn't totally disappear, does it? E to the 0 is 1, and then f, put 0 in for t. This looks like it's just f of 0. So I think, yeah, that's it. Negative f of 0. That's weird. So it looks like the linear transformation of a derivative is equal to, let me rewrite it backwards here, s f of s minus f of 0. And the f here is a function back in the t world. But if you put 0 into that function, you just get a constant, right? Yeah, looks right. Okay. So there's this business over here that we probably should address, and we'll talk about that later. It's called the exponential order. As long as your function is of this, what they call exponential order, then this thing will go to 0. If this was not of exponential order, then there's no guarantee that this whole thing might go to 0, so other things might be happening. So for our sake in our class, we're just going to stick with the exponential order. Now we also need to do like the second and third derivatives and stuff like that. So should we do one more derivative? Or should I just give you the function and the transformation and be done with it? I kind of have us all primed up for being able to do this, so let me... Or I could just tell you. All right, well, for derivatives, it turns out that there's a nice formula as well. And if you have like a higher order derivative, if you're doing this green work from scratch, you would have to do integration by parts multiple times. and then you can get your result. So instead of doing all that work, I can just tell you the solution. By the way, when we're transforming a differential equation, our differential equation is not usually written as f of t, right? It's usually written as y. So just as a slight change in notation, we can also write this as an L of y prime, assuming that y is in the t world. This is going to be equal to s, and then the corresponding letter for y is capitalized, so that's capital Y of s minus, and little y is back in the t world. We will put 0 into the little y function in the t world. So this over here, you would guess, should be coming from our initial condition or something. So for us to do something in the Laplace transforms, they're usually going to be paired up as an IVP, as a differential equation with an initial condition. All right. So this is for the first derivative, and you can do this for more and more derivatives and higher order derivatives and stuff like that. So in general, your formula looks like this. And this, again, would be obtained if you were to do the integration by parts several times. So let's just take an example. If we take the Laplace transform of y, the y triple prime. So this is the third derivative of y. So it looks like we're going to have an s to the whatever matching derivative is, to the third power, times your f, or I'm using y now. Y of s is the function that you're going to eventually solve for, minus, and then I'm going to start deleting 1 or subtracting 1 from the power of s squared, and then I have the original function y of 0. Keep the minus signs going. I have 1 less than the last one, so that's just s to the first power. And then I have a y prime at 0. And then the last one has s to the 0 power. And then we have 1 less derivative than 3, so that's y double prime squared, or y double prime of 0. So this, if you had a third order differential equation with an initial condition, because this is third order, you would have 3 initial conditions at the original function, the first derivative, and the second derivative. And that also all should come out as part of your problem. And you would fill it in when you do this transformation. All right, one more thing. When we did the derivative table, we had the derivative tables, right? And then at the end of the first semester in calculus, you guys started to talk about antiderivatives or integrals. And so how did you make up the integral table? You understand what I'm asking? You have this derivative table, which you learned throughout the first semester of calculus when you're taking derivatives. And then, at the end of that semester, you started to learn antiderivatives. And so you started to make an integral table. How did you make the integral table? Yeah, so you undo what you did for derivatives, so it's just the backwards, right? So it's just backwards. So it turns out that there's another transformation called the inverse transform. But the inverse transform, it could involve a complicated integral, But I think what we would be banking on is to look at your regular transform from t to s. And you have a list of those. We just made up a short list. And if you want to go backwards, you just look at that list and switch it around. Does that make sense? Just switching things around. So let me say a few things about the inverse transform. The inverse is linear. And the inverse transform looks just like the regular transformation transform, except it's written the other way. So I don't know if this is the best way to write a table. It's not. Usually, the table that you would see is just a two-thing table where you have f of t and capital F of s. And then you see the relationship to go from one way to the other. So in other words, 1 and 1 over s, t to the n, and n factorial over s raised to the n plus 1 power, e to the at, and 1 over s minus a, etc. So if you look at the back of your book or the appendix or somewhere, maybe the front cover, you'll see a table of Laplace transforms that would look like this. And it should just be clear that you go from one way to the other. That's the regular transformation. And if you go from your S world back to the T world, then that's the inverse transformation. So the key is to try to make, when you're transforming back, to try to make it look like one of these functions. Now the tricky part is that your functions may not look like that. Your functions may look really weird and complicated looking thing, but somehow, some way, through things like completing the square and partial fractions, you can somehow make this look like one of these transformed function in the S world that you can easily take back to the T world. Okay, so let me just put a couple more here. The sine kt goes to the k over s squared plus k squared, and then the cosine kt is the s over s squared plus k squared. All right, so this is it. This is a transformation. We haven't done any problems yet in differential equations. We'll do that as soon as we get back here on Tuesday. Okay. I haven't posted up the quiz yet, but you should be expecting a quiz on finding a power series solution on an ordinary point. I'll put that up, and I'll send a quick news forum announcement so you'll get it over email. All right, that's it. See you guys. Good luck with your homework. You have homework. You have power series solution homework due this Sunday, right? 6-1, 6-2.